All right, everybody, now we get into the meat and potatoes. Meat and taters. Okay, now we get to that part of the lab experiment that really kind of focuses and showcases what this class is all about. And this is a document that you have received with your lab directions and your data sheet. And this is going to be a summary of all of the, guess what, QC things that need to go on with the lab. So you are Miss Sally SOP, and you are walking into your desk and you're sitting down and you're like, okay, how can I make the lab staff miserable? No. But that's kind of what it feels like sometimes with the lab staff when they see Miss Sally SOP walking down the hallway. And, it could be Mr. Sally too, I don't know. Because, hey, one as bad as the other one. But either way, what's going to happen is that the QC department is going to sit down and they're going to say, okay, what are the things that's going to be needed to make sure that when this person runs these samples that we can trust the data, we can trust their work that they did in the lab, and we can trust the instruments work because we were not there. We did not see them do their job. We did not see the machine do that job. So what can we put in place to make sure that everything is kind of driving up, making sense, and that we feel good about it? And that is the purpose of this table and this document. All right. Now, I'm not telling you to stay away from quality control jobs, but they do have a reputation. And, a lot of times that reputation involves an eye roll when they see one of the quality people in a laboratory and they're like, oh God, what do we do now? But it should not be that way. The purpose of the quality team is to make sure that that company does not get audited and receive red flags, warning letters, 483s, and the other types of things that you're going to learn about in this course. Their job is drastically important, and it's to prevent mistakes when mistakes begin to happen. And then how can we prevent it in the future? So these are the things, very, very big responsibility. A lot of stuff falls on their shoulders, and that might be a great job for you. And I don't want you to stray away from them. But for some people, they just prefer to be in a lab. Just let me do some tests and call it a day. All right. All right. So this table is going to say a contract required detection limit, CRDL. All right, so contract. Okay, so someone's hired me to do a job, and they're going to say, Trace, I need you to run some stuff for TOC for me, and we're going to pay you a big fat check if you can do this for me, if you don't mind. And I'm going to say, okay, well, what kind of values do you require? Like, okay, your detection limit. How far do you want me to go down? How low do you want me to go in the game of limbo that we learned in Module 3? Okay, so with that said, they're going to let me know that information. And they're going to say, okay, well, what we would like to do maybe is that we would like to go with a 1 ppm. I would like for you to use a machine or use a method that will tell me at least a minimum detection that we would like for you to go to is going to be a 1. Based on our samples, based on what we know about what we should be expecting, you probably don't need to go anything lower than a 1. And I'm going to go, okay, here's the contract, now sign it. All right, so this is an idea of a CRDL. There are technical and contract holding times. So they're going to let me give me some information about what I need to be doing as I treat their samples, as I test their samples, as I preserve and store their samples. They're going to let me know what this information is supposed to be about. So what we're seeing in the table here is it looks like their CRDL is going to be a 2, not a 1. That's okay. And then it looks like 7 days from collection and 5 days from receipt at the laboratory. If we can test those samples in that time frame, then it looks like our preservation method is just cool it in a refrigerator, and we're going to protect it from sunlight and atmospheric oxygen. Okay, so it looks like that's going to be a pretty easy thing for us to do as a lab group together. This 4 degrees Celsius, this is again the temperature of a refrigerator, and notice it says plus or minus 2 degrees. So that means that yes, quality is going to require someone to take logbooks and data of our refrigerators probably on a daily basis. And we're going to go in and we're going to write down the temperature at that moment in time. We're going to sign it, we're going to date it, and we're going to initial it so that way they know who made that measurement. And sometimes sometimes it requires like a double check. But this is a way that we are keeping track of our refrigerator temperatures. So that is a thing, believe it or not, absolutely. These are very important things because they are specifically laid out in some of the methods or the SOPs that we have to follow. So we've got to do it. Next up, it says, well, you can go 28 days from collection or 26 days from the receipt at the laboratory if you preserve them, and you're going to preserve them with HCl or H2SO4. You got to get a pH that's lower than 2, so add a few drops of this stuff, swirl it, keep checking the pH, making sure it's okay, and then when you get something lower than a 2, then you can put them in the refrigerator and store them until you get ready to them. Okay, not a big deal, absolutely. I mean, we can do that. That seems pretty easy. Next up, it says, analyze all samples in duplicate. Dupes. Oh no, dupes. And it says all samples. All samples. So if a company donates 10 samples to the lab, and donates really the wrong word, they deliver 10 samples to the lab, every one of these samples will have to be duplicated, and that means we're actually running 20 samples in the long run. We've got like A's and B's or 1s and 2s. So everything is going to double depending on how many samples that are provided. Then it also says that duplicates should also include laboratory quality control samples. So everything that I'm running on my own that I've made that goes into the batch of samples, those should also be duped. Oh, no. No. So now what's going to happen is that if I had like a little measly 10 samples that were given to the lab for testing, and then I've made like 10 samples for quality control purposes, then that's going to be 20 in total. Everything gets duplicated, which means now my batch turns into 40, not 20. Very common, folks. I mean, this could be a thing, and a lot of people don't really anticipate this the first time they begin working in a lab, but all of these things are very important. Notice it says report the average and the relative percent difference in the reports when you begin to generate them and you begin to obtain this data. Now, I will say that for us, with the purpose of just demonstrating how this process happens, we do not follow things to the T. And we will dupe, absolutely, the samples that we will bring in. So, absolutely, we will dupe those. Cha-ching! Okay. Now, what we're not going to dupe, though, are the quality control samples that we have prepped together. So, we're going to place those into the auto sampler once. We're going to run them once, and we're going to wish for the best. That will save a little bit of time. That will allow us to process the batches faster. And depending on how many groups that are going to be doing this lab together, we can be held up for quite some time if we're not careful. So we can shave down, hours worth maybe of all of these quality control checks if we just run them one time and not twice. But keep in mind, that is a thing, and this tells me that is a thing that maybe should be done. Next up, it says calculate the sample result according to the EPA method. And it even tells me, look, report the sample results in concentration units of milligram per liter, aka ppm. That's going to be a question on Canvas, so you might as well get ready for it. And then as organic carbon, report the organic carbon concentrations that are less than 10 to 2 significant figures. So what this means is that if I go less than 10, like 9.8 is 2 significant figures, 5.1 is 2 significant figures, 4.0 is 2 significant figures. But if I go a second decimal after this number, that is 3 sig figs. That is not how this particular method wants them to report that data. And then if it says if it's greater than 10, then it's okay to go to 3 significant figures. All right, so why? Well, this is 10.1. That is 3 significant figures. 14.3, that's 3 significant figures. So what we're actually basically telling you here is that we want 1 digit after the decimal. That is how this is actually working out. So whatever digit that is, we keep one place, a tenth, the 10th placeholder. Everything else in front of that decimal we're going to keep. And it's just their way of wording it. So that way I know the proper way to put these numbers onto a report. By no means do I want to go in and say, oh yeah, we read your TOC and it read 22.431163100000. No, that is stupid. Somebody's going to look at this and say, you're fired. You're fired. You didn't learn anything while you were in school. Absolutely not. This is not appropriate, especially if your machine and our machine does not go that far in the first place. So no, that is not the way that this is going to work. Notice it also gives me a little of information about rounding, and it will say, hey, just follow the proper rounding rules, people. And just in case you don't know what the rounding rules are, let's say that I get a 10.643 because my instrument maybe goes to 3 digits. This is going to say, all right, well, this is where you need to stop that recording. So you need to say 10 point something. Look at the number after the 6. If that is greater than 5, round the 6 up. If it is less than 5, well, you keep the 6 as a 6 in this case. Keep whatever number that is as that number. So it tells me how to do proper rounding. Don't sweat it though, because a lot of the times your data will go into a spreadsheet. Excel will take over. Excel will round these values for you, and it will kind of prevent you from seeing too many significant figures on a report. So all of those things are going to be built in to the Excel spreadsheets when we get them. Next up is Table 2, and Table 2 is going to tell me a little bit about some of the quality control things that I need to keep in mind as I begin to do this lab experiment. First off is the initial calibration. So notice it says a blank should be ran and five calibration points. Our goal here, again with calibration back in Module 3, is to end up with a very straight line. And that straight line is going to be recorded as a regression coefficient. And I want to make sure that that R squared value is 0.995 or greater. Our machine does a very good job making these standards, analyzing them, and building a calibration curve. If you had to do this by hand, it does not matter. You need to meet that same criteria that we have in the table. So whether it's performed manually or by the instrumentation, it does not matter. That's the goal that we are after. If you do not get a R squared of 0.995, then folks, your calibration curve is not good enough. You need to go back to the drawing board. You need to try it again. You need to go rerun samples. And then only until you can get a calibration curve that kind of provides that data are you cleared out to use that calibration curve to solve for the samples concentration that we're going to be running. Very important, typically done first, typically reviewed. Make sure that this is making sense before we waste our time and go any further. Notice it says corrective action. If it is not 0.995, you're going to terminate the analysis. Everything just stops. Number 2, you're going to recalibrate. And then you're going to verify that it does meet 0.995 or greater before you go further in the analysis. So this means as a lab worker, if I go into an environment and I am manually doing this, and when I do it and I don't know what I'm doing, and I'm not being really careful with the pipetting, I'm not being really careful with the lines on the volumetric flask, I'm not being careful with the way that I mix and that I process these standards, folks, everything else cannot be done. I'm wasting my time. I'm wasting the company's time. Samples cannot get processed. We cannot report the data. It's just the way that it is. So basic lab technique is very important. And some people get very comfortable in the way that they do things. And they're like, oh yeah, I've got this. I've been doing this for 15 years. Okay, it doesn't matter because you could still not do it the right way that day. And you cannot process samples any further until you get an appropriate calibration curve here. So that is the iCal step. And notice it says the frequency is daily. You cannot use a calibration curve from last week. You cannot use a calibration curve from last year. For goodness sakes, it wasn't even done on the same day, probably not made with the same solvents. Everything in the environment is going to be different. Folks, you cannot do it. And this is why we require every group to produce their own calibration curve, to go through the motions of making a calibration curve. Even if we run your batches on the same day, it does not matter. We're going to make you go through the motions of making a calibration set so that way we can run them on the instrument. Every single day, if we did this for a living, it had to be done. Next up, number 2 is the initial calibration verification that we abbreviate ICV. We talked a little bit about this in Module 3, and notice it says it should be separate source, separate source, separate source from the iCal standards. Why? Why is that so? Okay. So let's say that I make my calibration standard, and I'm going to be making this from a more concentrated standard. So I go grab the bottle of 50 ppm in the lab, and I start to make them. Okay, that's great. What if that 50 ppm, though, was bad? What if it was contaminated? What if it was old? What if it was expired? What if it wasn't stored the proper way? What if it wasn't actually 50 ppm in it anyway? How would I know? I don't. Because if those things are bad, as I dilute them, then guess what? The bad parts of that sample or that standard that I am using, it's still there. It's still present. We're still diluting maybe the proper way. Maybe I am on task of where my pipetting is. Maybe I have double checked my lines on the volumetric flask. Everything went A-OK. I'm a stellar person employee. Give me a raise of 50 cents. Okay, well, if it's bad, you would never know. It doesn't really show up here. You can get a straight line, absolutely. But this straight line can be wrong because it's all crap stuff that you're using. And if you're using crap stuff in the beginning, then as you dilute them down, it's going to get crappy, crappier, crappier, crappiest. But it all lines up. It's all beautiful on a chart. It's all beautiful in a line. I would never know the difference. So that is why the initial calibration has to be coming from a separate source. So I could use another 50 ppm bottle here to make it, absolutely, but I want to make sure that it is coming from a different container than the one that they use to make the calibration start with. That's what this is all about. Things should be kept separate. We are double checking the cal curve. That is the purpose of the ICV. Notice it says that this should be done daily. This should be done prior to running any samples at all. And it should immediately follow the standards that you have ran for the calibration curve. So we run calibration first, making sure that looks okay. If it does look okay, we're not out of the woods yet, Taylor Swift. So now we're going to look at our ICVs. And when we look at our ICV, we're double checking that calibration curve. I know what I made. Is that the number that's popping out onto the report? I hope it is. I get a 10% window for that. Whatever value that the ICV should be, you get a plus 10% and a minus 10%. That is the acceptance window. So again, if you've got a calculator on your phone, very easy calculation to do. You just open up your phone, make sure that you're in kind of the basic calculator, no bells or whistles at all. And let's say that your ICV is supposed to be a 6 ppm. Well, you're going to key in 6 to your calculator, and you're going to put plus 10%. And then you're going to key in and hit enter, write down that number. And then you're going to hit 6, and then you're going to do minus 10%. Write down that number. And that is your window. This value should fit within that window. So 10% of 6 is what? 0.6. So I can go 6.6, and I can go down to 5.4. That is my window of acceptance. Notice it says, if things don't work out, re-prep the ICV. Reanalyze everything if needed. Identify and document the problem. Oh, documentation rules. We'll talk about that in modules. Then it says recalibrate and reanalyzed the re-prepped ICV all over again. Hopefully everything goes smoothly this time. And then if it does, move on to your samples. Folks, this is a hurdle. If I make a calibration curve and I can't get a 0.995, I stop. I can't do anything else. If I make a calibration curve and I do a 0.995 and I feel good about it, then the next is the double check. And that ICV is going to be reporting a value. And if that reporting value is incorrect and it does not fit within plus or minus 10%, then it's a hurdle. I stop everything that I'm doing. I can't go any further. That's because my calibration curve has not been verified. It's not been checked. That's the purpose of the ICV. Next up, number 3 is carbonate by carbonate. Well, guess. Okay, so I'm getting rid of all of that. We don't need to worry with it. And the reason is because I just don't want to overcomplicate this stuff to make it even worse. So we're just focused on TOC standards, making some standards, running some standards, and running some samples. Next up, continuing calibration verification. This is known as CCV. Again, module 3, I learned lecture. Good for you. So this looks like it should be analyzed before the samples, and then after every 10 samples, and then again at the end of a run. Some people will call this ending one the ECV, which is the ending calibration verification. Just to kind of make it clear, this is where samples stop in this batch. As before, plus or minus 10%. Number 1, if it does not work out, we're going to recalibrate and verify. Number 2, we reanalyze all the samples back to the last good one. Oh, God. What does that mean? All right, well, let me give you an example. We do iCal. 1, 2, 3, 4, 5. And what we get, straight line. Yay! Next up, we're now going to do an initial calibration verification, an ICV. When we run it, we get a number. That is processed like a sample. That is going to go into the calibration curve. We get a number based on the calibration curve that we've generated, and it gives me what that value is. That value better match. Cha-ching! Works out great. We're within the threshold of 10%. Okay. Oh, I'm feeling good. All right. Yeah, I did my job. My standards are working. I'm not actually ran any samples yet, but it's there. Good news for you. Next up, it says in the table, then you're going to do a continuing calibration verification, a CCV. You're going to make it. You're going to run it. And just as before, you get a number. There we go. As before, 10% plus or minus. And let's say, cha-ching! I get it! Woohoo! Okay. All right. I see. Now, after that table, when we explained it, when we looked at it just now, it says, okay, you're going to do this before samples. We did. But then it says you're going to do it after every 10. So I now go into my samples. 1, 2, 3, blah, 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 10. If I have more than 10, then I need to make a break. And I need to go back. And I need to run CCV again for a second time. This is a continuing. Well, who would have thought that's what the C meant for continuing? It is a continuing check that we are doing throughout the batch. So when I go in and I do this continuing check, well, it can be the same thing. It can be the same number. Cha-ching! And let's say I run it, and this time, oh no! What do I do? What this table tells us, and the thing of quality control, is that, all right, you cleared it out in the beginning, but folks, something happened here as the samples were running. You were running 10 samples, and throughout this time, something was questionable, and something became a little different, because here it did not pass. And what this means is that when we look at the CCV for 1, and when we look at the CCV for 2, I can't report any of that data. It needs to check out in the beginning of that section and at the end of that section. And if it does not do that, then we're going to have to go back to the drawing board, and we're going to have to remake maybe CCVs or recheck the CCV to make sure it's still making sense, because something happened along the way that was a problem, and that continuing check was able to pick out that problem and that it happened. And it's telling me that on the report. So nothing can be reported here at all. All right, well, if that's the case, then let's get rid of my and then let's say that I run the CCV number 2, and when we run the CCV number 2, we get a cha-ching! All right, yeah, woohoo! I'm off to the races again. All right, so what this means now is that my first one checked and my second one checked, and that means all the things in the middle are a cha-ching, cha-ching, cha-ching. All right, okay, that makes me feel really good. But maybe my batch is not complete. Maybe there's more samples, and there will be. So now what's going to happen is that from this moment, okay, now that's going to happen is that samples are going to be re-ran or continue to go through the batch, and we're going to start with maybe number 11, and then we go 12, 13, 14, 15, 16, 17, 18, 19, number 20. Good job. And then, because of that, the way that the table's made, the idea is that we need to continue to check. All right, CCV, this time number 3. And just as before, I get a number. Does that number fit in the window threshold of a plus or minus 10%? If it does, woohoo! Party time! I get to pass all of samples 11 through 20. One step in the right direction. Absolutely, we keep on trucking. Feel really good about it. But if CCV3 fails, and again, you know what I'm going to do, then I'm going to say, oh no! Because CCV number 3 failed. CC2 actually passed. So the beginnings of it worked, but something happened in the middle to make it lose control. Was that a Madonna song or a Janet Jackson song? Maybe Missy Elliott. So what this means is that everything in this section now, can't report it. That's the purpose of a quality batch, folks. These are the hurdles that we have to make it through, because all of these checks are in place to make sure my instrument and my procedure is going according to plan. And if I cannot introduce quality checks, then I cannot trust the data that the machine and the procedure is basically providing me on a fancy looking report. It's got to be here. You cannot lie. You cannot fudge. You cannot make up data. You can't pretend like it has happened. Absolutely not. You need to be fired if that's what goes on. So that is why in number 2, it says you're going to reanalyze the samples back to the last good CCV. Everything up until that point has tended to go okay, Maybe that third one you didn't get luck with. So we maybe need to recalibrate. Maybe we need to verify that that calibration's working. Maybe we need to check that standard that was prepped to make sure it is what it says it is. And then we're going to reattempt it all over again. That's number 3. The next video, we're going to pick up from here. We're going to talk about the next couple of line items, more about quality control, and why these things are so important. So I think that now you're getting a little bit of flavor of how this lab is going to be somewhat different. A little different than if you've taken 114, a little different than what you've seen so far in the beginning of the course. We're now digging a little bit deeper into deeper. What's deeper? You're probably deeper because you're listening to my videos all the time. So in the next video, we'll get even deeper